Hey, welcome back. This is Calc 2. We're on to our review for Test 3, just covering integrals. And let's start out with 8.1. Take a look. Just a reminder, this test will be a written test. You'll basically log into your WebEx. I'll post the test in Blackboard. You'll download the test. I'll still need to come around and check everybody's work area, their scratch paper, and their calculator. I'm still debating whether or not you can use a graphing calculator on this test. I'm really leaning against it, as I know some of the calculators can do integrals, and that would be, here's the answer. No, I can't do that. So I'm still debating on that. Whether I'll let you use calculators, I will let you know. Worst case scenario, I'll let you use a scientific, but not a graphing calculator. So anything with a big screen is going to be kind of off limits. And even some of the ones that have littler screens, or as long as they can do integrals, those will be off limits. So, okay, so without further ado, anyways, let's kind of jump in here to 8.1. We're looking at just basically any kind of integral you can imagine. I kind of go through and browse the questions and see if there's something that looks unfamiliar to me, and then, this is how you should approach it, right? If there's something in there that looks unfamiliar, you probably want to do it, unless it's really, really difficult, because I'm probably not going to put really hard questions on the test. Like I'm not going to pick number 69, odds are. I'll keep it to the more medium level questions. So 21 isn't a bad guess. So anyways, I'm going to do a U sub on this in the denominator, because you want to cause a cancellation. This one is kind of like if you've not done this problem before, it's maybe not obvious what the cancellation will end up being. So let's look at it. du is negative 3t squared plus 9 dt, and then you could divide out dt for solve for dt. So you get du over negative 3t squared plus 9. Okay. So if you do your substitution, t squared minus 3, we'll have a u down here, and then du all over negative 3t squared plus 9. But it's not clear how that cancels. You could factor out a negative 3 from that denominator, right? So you'd have a negative 3 times t squared minus 3, and then you have the cancellation, right? So all I did was just take this guy here, and in the denominator factored out a negative 3 to make it possible for me to get rid of all the t material, right? Okay. Once I'm done with that, I can factor out any constant. So you have a negative 1/3, and then the integral of du over u, which is just a natural log. So negative 1/3 ln absolute value of u plus c. And that'll be negative 1/3 ln absolute value, and then you back sub. So if you begin in t, you have to end in t. And there you go. All right, let's look at another one. So remember, there's going to be some formulas you kind of need remembered. So obviously we need, the ln integral. The integral 1 over t is ln of absolute value of t. This one turns out to be inverse tan. So you definitely need, the inverse tan formula, the inverse sine formula. You need to know how to do completing the square. You need to know how to do long division. So let's take a look at this guy. Okay, I got to complete the square on this guy. You can factor out a 4 from the first two terms. You get x squared plus x, and then you're going to complete the square and immediately subtract 4 times whatever you add in, and then plus 65, and that's all dx. So to complete the square, you take the coefficient in front of x, which is 1, and then you divide it by 2, and you square it, and then you're going to put that right there. Okay, so that's 1/4. The thing that goes over here, though, is not 1/4, right? It's really 4 times the 1/4 that goes there. So that would be the 1, and then plus 65. Okay, let's go ahead. We complete the square. Let's go ahead and factor it. So you get 4 times x plus 1/2 plus 64 dx. And that pesky 4 in the numerator can now be canceled with the denominator. you just factor it 4 out of the denominator. You get this expression. And then you have a nice little cancellation. Boom, boom. And it's turning into a nice, this should be squared, sorry. It's turning into a nice inverse tan, right? So the u here is the x plus 1/2. Of course, du is just dx in this case, so dx is du. The a value is going to be 4, and we'll end up with 1 all over 4 tan inverse of u, which is x plus 1/2 all over a, and then plus c. Okay. Usually try to get rid of these ugly complex fractions that you see inside the tan inverse. On a written test, I'm not too worried about you simplifying, but in the heat of battle, I know that sometimes you forget to do things. So leaving your answer this way, you know, as long as you got the integral, I'm usually psyched. But it's kind of a relative thing too. So I kind of look at what other students are doing, and you know, did you do better than them or did you do worse than them? That's kind of how I think of it. But anyways, let's say it's 63 and see what's going on there. So now this is actually a definite integral, which means we have to go ahead and evaluate at the end step. We have x plus 1 in the denominator dx. There may be some question as to whether or not this is ln of x plus 1. My pen is freaking out on me. I don't know why. X plus 1, maybe it has something to do with my mouse. Yeah, it did. All right, so x plus 1 cubed, or is it ln of x plus 1 cubed on the inside? And it turns out to be this one. How would you know? Well, if it was everything cubed, you would see it like written like this. Okay. Okay. So first I'm going to use a power rule to kind of break it down a little bit, and you get 3 ln, the power rule of natural logs. So you could always take this exponent here and plop it in front of the natural log. And that's all over x plus 1 dx. Hopefully I don't forget to integrate. Here you can do a u sub for the natural log, and my mouse is flipping out again for some reason. Okay, so over here you could do a u for the natural log of x plus 1, because du is going to be 1 over x plus 1, and that'll cause your cancellation. So 1 over x plus 1 dx, and then dx is x plus 1 du. Okay. Okie dokie. So we have 3 times the integral of u all over x plus 1, and then times x plus 1 du, and you see your cancellation there. Boom, boom. And you're being left with 3 integral of u du. That's just a power rule. So you get 3u squared over 2. I have to remind myself to evaluate. I'm going to back sub first. You can't put 2 and 3 into this thing. You would have to change the limits of integration. So I just like to back sub it. So 3/2 times ln of x plus 1, and this whole thing's squared from 2 to the 3. There's not much you can do with the answer. You can get an approximation. I prefer if you just put those numbers into the natural log. So you'd end up with ln of x, 3 plus 1 is 4 squared, minus 3/2 ln of 3 squared. And you just leave your answer like that. No reason to go to your calculator. That's as good as it's going to get. Let's look at 8.2. And 8.2 was on integration by parts. I'll be picking problems from the set 15 to 33, and then 43 to 51. Is that kind of what I did up here? Did I give you yeah, I gave you problems. Okay. Let's look at a later one, 43 first. I think this one's a little easier, and then we'll look at the other problem I have for us. So here I have xe to the x over 2 dx. We have to evaluate this guy. You can use the tabular method that I do the video for, or you can use the u's, v's, and dv's and stuff, whichever one. Please use one of my methods, though. Don't have the web do it for you. So anyways, u is liate, right? So you do algebraic first. So algebraic and then du is just dx. dv, of course, is e to the x over 2, and then dx, and then, of course, v is equal to 2e to the x over 2. You would have a u sub x over 2, dx would be 1/2 du, and then if you multiply both sides by 2, you get that. Okay, so we have this times this, uv, so 2x e to the x over 2, minus this, the integral of that times that. So you can factor a 2 integral e to the x over 2 dx, right? And I have to remind myself to evaluate. Okay, so I'll have 2x e to the x over 2 minus, and this integral of e to the x over 2, we kind of already did it in this box. So it's going to be 2e to the x over 2. But there's another 2 in front, so it's going to become negative 4e to the x over 2, and then I have to evaluate from 0 to 3. Okay. So the first one's going to be, when I plug 3 into the antiderivative, I get 6e to the 3 halves minus 4e to the 3 halves minus, now plug 0 into the antiderivative, you get 0 minus 4e to the 1, which is 1. Okay. You can combine these. These are like terms, so you get 2e to the 3 halves plus 4 is a reasonable answer. You don't need to get me an approximation. Okay, that's good enough. Let's look at one that's a little harder. This is one of the loopy ones. E to the negative 3x sine of 5x dx. Okay, so sometimes you have to do it multiple by parts. With this one, it's multiple by parts, but then you kind of end up back where you started, if you remember doing this. So let's take a look. Liate says trig before exponential, and then we'll have our dv is e to negative 3x dx. Okay. So v is negative e to negative 3x, this time divided by 3. And then du, there's a chain rule involved, produce a 5, and then cosine of 5x. Okay. Okay. As usual, u times v, so this will be negative e to negative 3x. You want to put exponentials in front of trig functions, mainly because if you put it behind sine of 5x, if you have sine 5x e to the negative 3x, people might think that that e to the negative 3x is inside your sine function. So if you put the e to the negative 3x first, it just looks better. Okay, and then that's all over, 3, and then minus a negative. So plus, we'll have 5/3 integral of e to the negative 3x dx. And then, whoops, and then, you know, it's v du, so I lost my du part. Whoops. So cosine 5x dx. And then I have to do by parts again, right? Because this thing, I'm not going to be able to integrate it. So this time, Liate says trig before exponential again, so 5x, and then my dv is going to be e to the negative 3x again, dx. V will be negative e to negative 3x over 3 again, and du with a chain rule, negative 5 sine 5x. Okay, so there's that chunk. At this step, then, we'll have negative e to negative 3x sine 5x all over 3, and then plus 5/3 times another by parts, right? So u times v is negative e to negative 5x cosine of 5x all over 3. I'm starting to smush this in. Minus negative negative is minus a positive, so just minus at the end. And then there's a constant of 5/3 integral e to negative 5x. Whoops. My 3x has morphed into a 5x. So negative 3x actually. So e to the negative 3x sine of 5x, and then dx, and then all of this is in parentheses. There'll be a plus c there eventually. The point here now, though, is to recognize that what you've produced here is kind of where you started. And that's the trick you want to take advantage of now in the book. You'll equate, so you're going to take this side here and equate that to this thing here, right? And then you're going to replace this integral and this integral with letter I. Okay, so let's do that. So I'll have I equals, I go back to the white pen, so I equals negative e to negative 3x sine 5x all over 3. Then minus, when I distribute this 5/3 to both terms, minus 5/9. In the numerator, there's an e to negative 3x cosine of 5x. And then minus 25/9 I. Right? And then there's a plus c eventually. Okay. So move the minus 25/9 I to the other side. Common denominator, 9/9 plus 25/9 is 34/9. I equals all this stuff. And then multiply both sides by 9/34. Okay, so you end up with I, the integral equaling, if 9/34 times 1/3 is 3/34, so negative 3 e to negative 3x sine 5x all over 34 minus 5 e to negative 3x cosine of 5x all over 34, and then plus c. Okay, one of the weird loopers. I used to call those loopers. All right, let's move on to 8.3, where we kind of gave you an overview of trigonometric integration. In 8.4, the trig subs kind of turn into these types of problems. So let's take a look. So number 7, integral of sine cubed x cosine squared x dx. So this is one of those ones where you kind of have to push back one term or one factor. So if you push back one factor of sine, you'll end up with this. And then you could do a Pythagorean identity on sine squared. Replace that with 1 minus cosine squared. And then you could replace all the cosines with a u sub. Okay? And then du is negative sine x dx. And of course, dx is negative du over sine x. Okay. So I'm going to zip through here and replace. So I get 1 minus u squared times sine x times negative du over sine x. And then I need some cancellations. So sine x, I'm going to distribute the u squared. I'm going to bring the negative along for the ride when I do my distribution. So I'm going to distribute the negative u squared into here. Okay. And you'll end up with the integral of negative u squared plus u to the 4th du. And then you can do power rules. So negative u cubed over 3 plus u the 5th over 5 plus c. And then you back sub cosine. Okay. So negative cosine cubed x over 3 plus cosine the 5th power of x over 5 plus c. Okay. Okay. There was a bunch of sort of trig identities I gave you to memorize in this section. So this next problem, you kind of have to apply one of those trig identities. Let's see what we have, 3x dx. Okay, so this is the one, cosine squared is equal to 1 plus cosine of 2 times whatever the angle is. So it doubles the angle, 6x all over 2 dx. And we can factor out 1/2. So you have to know those identities. 1 plus cosine of 6x dx. And then that'll be 1/2 x plus sine of 6x all over 6 after you do a u sub plus c. And then you could distribute your 1/2 and have your answer. So you have x over 2 plus sine of 6x over 12 plus c. Okay. Okay. Let's look at this next one. This next one's a little bit longer. Well, obviously it's a trig sub, so it's going to be long, but it's a little longer than probably what I would want to put on a test. And so just be aware, I'm not going to put anything that's too crazy, but at the same time, pretty much all trig subs are kind of crazy, right? So let's look at, oops, I want to look at, I want to look at number 5 and then number 9. The number 9's the crazy one. Number 5 has some elements in there I don't like either, but I didn't want to have to sit around doing 20 trig subs just to find an appropriate guy. Don't worry, I will for the test, but for the review, I just didn't have time to pick and choose. So anyways, based off the form, you can see it's a sine. So x equals 4 sine theta. And then, get your dx. So that's going to be 4 cosine theta d theta. And then get your triangle stuff. So theta is sine inverse of x over 4. So my triangle, opposite over hypotenuse. And then we get the square root of 16 minus x squared. And all of this junk gets cordoned off there. Okay, so let's take a look. I got the integral of the square root of 16 minus x squared, so that'll be 16 sine squared theta, all over x, which is 4 sine of theta, times dx, which is 4 cosine theta d theta. Already I can see there's a nice cancellation there. Inside the square root, let me kind of do that in my head, the stuff under the square. So I got the square root of, I can factor out 16 and get 1 minus sine squared, right? 1 minus sine squared from the Pythagorean identities is just cosine squared. And then take the square root of that. So you end up with 4 cosine theta all over sine theta, and then there's another cosine theta, so that's be cosine squared theta d theta. Okay. Won't be able to do a u sub on that. The best you can kind of hope for is maybe, well, maybe I don't want to do a u sub. This is weird, isn't it? So what I can see is a cosine squared. I'm going to have to retranslate that into 1 minus sine squared theta. And then I could bifurcate or butterfly that fraction, right? Okay, so that would be 4 integral 1 over sine theta minus sine squared theta over sine theta d theta. Then this integral will turn into 4 integral cosecant theta minus sine theta d theta, and then this will turn into, and here's an issue right here. I wouldn't expect you to have the antiderivative of cosecant memorized because it's so annoying. I would have given that to you on the test, but just for here, it's ln absolute value cosecant theta minus cotan theta, and then minus 4 times the integral of sine is negative cosine, so this will become plus 4 cosine theta, and then plus your integration constant. This is like half the battle right here. The problem is we still haven't used our triangle, and that means we have to use a triangle to do to get everything back in terms of x, right? So 4 ln absolute value. Cosecant is actually 1 over sine, so it's going to be hypotenuse over opposite, so that'd be 4 over x. And then minus cotan is adjacent over opposite, so square root 16 minus x squared over opposite x. And then plus 4 times cosine, which is adjacent over opposite. So square root 16 minus x squared over opposite plus c. And then you could simplify that at least a little bit. 4 ln absolute value, I guess there's a common denominator there. It's not necessary to do this part, but there it is. Plus the square root of 16 minus x squared plus c. That'd be as good as I would want it. Okay. Okay. I had one more, but it's literally way out there, and it's kind of long. I don't want to do it. I'll probably give you one this along these lines here. If I require to use a weird formula like the cosecant one, I will give that to you on the test. I will give you, but any of the ones, you know, I've said previously that you should have memorized, you should have memorized, and I'm not going to give you those. Okay, so let's move on. That's enough of that. 8.4, let's go to 8.5, which is on partial fraction decomposition. So 8.5. Yeah. So we got 3 to 19. Let's look at let's just do two of these. Let's look at number 7 first. X squared plus 12x plus 12 all over x cubed minus 4x dx. So the point of these was to take a rational function like we have here and turn it into a bunch of little fractions that we can do natural logs with or inverse tans with. So let's do the partial fraction decomposition. So x squared plus 12x plus 12 all over x cubed minus 4. So let's go ahead and factor that. What is that going to be? X times x squared minus 4. That'll be x times x minus 2 times x plus 2. Okay. So let's just cut to the chase. Okay. So x times x minus 2 times x plus 2 equals a over x plus, these are all linear factors, non-repeated, so I can just put ABC in the numerators. There'll just be 3 of them. Then I want it to multiply to get rid of all the fractions, so multiply both sides by x times x minus 2 times x plus 2, x times x minus 2 times x plus 2. Okay, so on the left, all the fractions cancel out. And then on the right, one term of the factor that I'm using for the distribution will cancel in each distribution. So I'll have ending up with a times x minus 2 times x plus 2 plus b times x plus 2 plus c times x minus 2. Okay. And then we're going to, I think we'll just do substitution this time. Like we had 2 methods, equating coefficient and substitution. Equating coefficients always works, but substitution is often faster. So I'll do this one, substitution, and the next one, equating coefficients, okay? Okay, so here we go. I'm going to try x is 2, and then on the left-hand side, I'll have 4 plus 24 plus 12. On the right-hand side, if you put x is 2 in there, the first one will be 0 and the last one will be 0. And then the second one will be b times 2 times 4. So what do I have? 36 plus 4 is 40 equals 6b. And then b will equal this is 8, not 6. Then b will equal 5. Let x equal negative 2. Okay, so I'll have 4 minus 24 plus 12 on the right-hand side. Looks like the c term is the only one that doesn't cancel out. So c times negative 2 times negative 4. Okay, so I get negative 12 plus 4 is negative 8 equals positive 8 times c. So c is negative 1. Excuse me. And then finally let x be 0. So we got 12 equals a times negative 2 times 2. So 12 is negative 4a, and then a is negative 3. Okay, great. So we can rewrite our integral now. So our integral will be negative 3 over x plus 5 all over x minus 2 minus 1 all over x plus 2 dx. Let's make sure I put them in the right places. So a goes first, negative 3, and then 5, and then negative 1, yes. Okay. These then are just natural logs, so negative 3 ln absolute value of x plus 5 ln absolute value x minus 2 minus ln absolute value x plus 2 plus c. There he is. That's it. Okay, let's move on. So one where we do equating coefficients. So 15. 9 minus x squared all over 7x cubed plus x dx. Okay, so partial fractions again, so 9 minus x squared all over, I'm going to factor the denominator, get an x out there, so I get 7x squared plus 1. Okay, so I need 1 for the linear factor of x. I need one fraction for that, so that'd be 8 over x. Then I need one fraction for 7x squared plus 1. So I need, in that case, a linear term in the numerator. Okay. And then I have the irreducible quadratic in the denominator. Okay, first things first, get rid of all the denominators, multiply by the denominator of the left-hand side. Okay, so I end up with 9 minus x squared equals, and I distribute, so I get a times 7x squared plus 1 plus 7x squared plus 1's cancel, and I got bx plus c times x. Okay, I'm going to rewrite the left-hand side so I can see the coefficients a little better. Negative x squared, there's no coefficient for x, and then plus 9. On the right-hand side, I'll have 7ax squared plus a plus bx squared plus cx. I'm going to group all the like terms together and factor. So I get negative x squared plus 0x's plus 9 equals 7a plus b. It's really 7ax squared plus bx squared, but you can factor an x squared out of those two. This way we can see the coefficient, right? And then plus cx plus a, and then you're equating the coefficients. So on the left here I have a negative 1, okay? And then on the right I'll have a 7a plus b. So it's 7a plus b equals negative 1. On the left, for the x term, I have 0. On the right I have c. So c, yeah, sometimes can be 0. And then a must be 9. Okay. Okay, so I just need to find what b is. So I take the a value and plop it in here. 7 times a is 63. So b is negative 1. And then that'll give me b equaling negative 64. It's a big weird number. Okay. Okay, so now I can go back and rewrite my integral. That's going to be 9 all over x minus 64x plus 0 all over 7x squared plus 1 dx. And then the first guy's done, right? That's just a natural log. The second guy will require a u sub on the denominator. And then we're going to get a funky constant. Okay. So I get the integral of 9 over x minus, well, let's 9 over x dx minus 64 times the integral of x over u times du, which is times dx, which is now du over 14x. So a little bit of cancellation there. We can bring out the 14. So I'm going to end up with 9 ln absolute value of x minus 64 over 14 is the same as 32 over 7. And then you have the integral of du over u, which is another natural log. A lot of natural logs result when you do these kind of problems. So it's 9 ln absolute value of x minus 32 sevenths ln absolute value of u. Let's go ahead and back sub. This is 7x squared plus 1 plus your integration constant c. Okay. Okay, so that's equating coefficients. Let's move on. So I'm going to skip over 8.6 and 8.7. 8.6 was on using tables and integration methods, or was it numerical methods? I think it was the tables section. Then I'm going to skip over the numerical methods. I might make that like a bonus problem for this next test if I remember. But let's look at 5.6. So this was on L'Hopital's rule. You're taking anything from 7 to 61 odd, and So basically, there's 4 types of problems. There are ones that are just pure L'Hopital rules. So you get the limit as x goes to infinity of ln of x over x squared. If you look at plugging in infinity into each, ln of infinity, that's going to go to infinity. Real slow, but it's going to go there. X squared will also go to infinity. So if you have 0 over 0 or infinity over infinity, you can apply L'Hopitals. Derivative of ln of x is 1 over x. The derivative of x squared is 2x. So you end up with the limit as x goes to infinity of 1 over x divided by 2x, which is the same as multiplying by the reciprocal of 2x, which is 1 over 2x. And then you have the limit as x goes to infinity of 1 over 2x squared. And that's L over infinity, which is always 0. Okay. Let's look at another one. So this is 46 in the book. Limit as x goes to infinity of x tan of 1 over x. Okay. So in this case, if you let x go to infinity, inside the tan of x, you have 1 over x. So 1 over x as x goes to infinity is 0. And then the tan of 0 is 0. Okay. If you let x go to infinity, that will go to infinity. So the form is infinity times 0. And the trick for those forms is usually to rewrite it as a complex fraction. In other words, write tan of 1 over x all over 1 over x. Okay. Once it's in that form, it's really an infinity. It's really a 0 over 0, right? 1 over x as x goes to infinity is 0. Then the tan of 0 is 0. And then the denominator, that's also 0. So now we can do the L'Hopitals. So I'm going to get the limit as x goes to infinity of the derivative of tan is secant squared. 1 over x. And then the chain rule, the derivative of 1 over x is negative 1 over x squared. Same for the denominator, derivative of that, negative 1 over x squared. Nice cancellation results. And then you're going to end up with the limit as x goes to 0 of secant squared of 1 over x. Infinity, not 0. Okay. As x goes to infinity, 1 over x goes to 0. And then secant squared of 0 is just 1. Because secant is 1 over cosine. Cosine of 0 is 1. 1 squared is 1, so it's just going to be 1. Okay, great. Let's look at another one. So 53. We have the limit as x goes to 0 from the right of 3x to the x over 2. Okay, this is a 0 to 0 power, which is one of our weird forms. So the deal for this one, I said to bring the limit inside the exponential. So you're going to first convert this thing into an exponential. Okay, so limit as x goes to 0 from the right of 3e to the x over 2 ln of x, right? Because originally you can rewrite this thing in the box as e to the ln of x to the x over 2, and then you could take this thing and put it in front, and you end up with this thing. Okay, so I'm going to pass the limit into the exponential, and I get 3e to the limit of x ln x over 2 as x goes to 0. And what is that form? Well, if you plug 0 in for x, you just get a 0. If you plug 0 into the ln of x, you're going to get negative infinity coming in from the right. Okay, the ln of x will go to negative infinity. So you have another 0 times infinity form. You can remedy that by doing a complex fraction and then doing L'Hopitals. So let's do that. I have ln of x all over 1 over x. Then I could do the L'Hopitals. 3e to the limit of as x goes to 0 from the right of 1 over x all over negative 1 over x squared. Then that will be 3e to the limit as x goes to 0 from the right of negative x squared over x, which is just negative x. And then you could do a substitution to evaluate that limit. It will just be 3e to the negative 0, which is 0. In other words, 3 times 1, which is 3. Okay. So there's that type. The only other type is this infinity minus infinity type. So let's look at that. I'll probably put one of each on the test. So we have the limit as x goes to 1 from the right of 3 all over ln of x minus 2 all over x minus 1. Okay. So the first guy, as x goes to 1 from the right, ln of x will go to 0 from the right. So it's going to go to positive infinity. Minus, as x goes to 1 from the right, you'll have 2 all over something really small positive. That will go to infinity as well. Okay, so the remedy for this situation was to just make a common denominator. Okay, so you'd end up with 3 times x minus 1 minus 2 ln x all over x minus 1 times ln x. Okay, and then if you plug 1 into that, you're going to find, well, hey, that's 0 minus 0, so the numerator is 0, and the denominator 0 times 0 is 0, so you're going to have to apply L'Hopital's. Okay. So in the numerator, if you distribute, you have 3x minus 1 minus 2 ln x. If you take the derivative of that, you're going to end up with 3 minus 2 over x. In the denominator, this thing is x ln x minus ln x. Taking the derivative on the first term, you need a product rule. Okay, so leave x alone times the derivative of ln x is 1 over x. And then minus, or rather plus, the derivative of x is just 1. And then ln x is just left there. And then minus the derivative of ln x is 1 over x. Okay. That thing is then determinate, believe it or not. The numerator, if you plug in 1, you'll just get a number. You'll get 1. Okay, so you get some number L. And the denominator, if you plug in 1, what are you going to get? You're going to get 0. So the only question is, are you going to get positive or negative infinity? And the way to remedy that is just to plug in some number into the denominator, like 1.1, something that's to the right of 1, because we're coming in from the positive direction. Right? We're coming in this direction. So do a test value of 1.1. Okay, so this is 1 from the right of 3 minus 2 over x. Let's clean it up a little bit first, right? So I'm going to put that ln x first, because you put 1 in there, it's just 0. And then plus 1 minus 1 over x. Okay, so if you put 1.1 in there, this is just going to be some positive number. This part then is going to be 1 minus 1 over 1.1. So this is going to be positive. This will also be positive. A positive plus a positive is positive. So in other words, it's going to go to the positive infinity. Okay. Let's look at 8.8. 8.8, we had improper integrals of 2 types. The problem set is 17 to 43. We had the infinite interval and the infinite discontinuity. So let's look at one of each. First, the infinite interval. So we have e to the x over 3. It's kind of an easy one. We need to replace the bad limit on the integral with a variable, and then take the limit as the variable approaches whatever the issue was. So here the issue is going to infinity. Okay, and then we just do the integral, okay, as usual. Sort of forget about the limit for a little bit. The integral of e to the x over 3 is 3e to the x over 3. We're evaluating from 0 to b. This will be the limit as b goes to infinity of 3e to the b over 3 minus 3e to the 0, in other words 3. As b goes to infinity, this part is going to go to infinity. So it'll be equal to infinity minus 3, which is just infinity. And then you have to note it's divergent. Okay, let's look at one of the infinite discontinuity problems. This one's a little bit longer. 37. Going from 0 to 1 of x ln x dx. So the issue here is at 0, because you can't put 0 on the ln of x. ln x is not defined at 0. Okay, so we're going to have to take the limit as we approach 0, but we have to be careful about the direction of approach, right? So what I taught you to do is kind of think of a running man in between 0 and 1, and then we have to go to the discontinuity, and in the direction that we are going from the little picture, we're coming in from the positive direction, so that will be b goes to 0 from the right. Okay, replace 0 with b, and then you have x ln x dx. So I got the limit as b goes to 0 from the right, and then you just have this integral to kind of chug out. Right? So that's a by parts. U is Li8 ln x, du is going to be 1 over x dx, and then dv, of course, is just x, and then v is going x dx, if you wish, and then v is going to be x squared over 2. So u times v will be x squared ln x all over 2, and then v du, the integral minus the integral of v du is 1/2 integral of x dx. I have to remind myself to evaluate. Okay. So this will be the limit as b goes to 0 from the right of x squared ln x over 2 minus x squared over 4 from 0 b to 1. Okay, so let's plug in those limits. So I get the limit as b goes to 0 from the right of, plugging in 1, you get 1 times ln of 1, which is 0. So you just get 0 over 2, which is 0, minus 1/4, minus b squared ln b all over 2, minus b squared over 4. So the troublemaker is definitely this guy right here. Okay, its form is 0 times infinity, negative infinity in particular. So we're going to extract that one little guy and see where it goes. Okay, the other ones, this one's a constant. This one will just go to 0. Okay, so is this guy in blue that I need to worry about? So we have b squared ln b all over 2. And the trick is to, because the b is going to 0, the b squared will go to 0, and the ln of b will go to negative infinity from, if we're approaching from the right. Okay. So yeah, I have to do my trick, and the trick in this, the trick we learned is to turn it into a complex fraction, so you can apply L'Hopital's, right? So this will be negative infinity, and this will be infinity. All right, so I go limit of 1 all over b all over negative 4 all over b cubed. So that'll be the limit, if you multiply by reciprocals, negative b cubed over 4b, which will be negative b squared all over 4. And then remember, your limit is going to 0. Okay, so that's just going to be 0. In other words, this thing will be 0. In other words, this thing will be 0, and we're just left with negative 1/4 for our answer. Okay, so that'll equal negative 1/4. In other words, it's convergent. Okay, cool. So we know it seems like a lot, but this integration stuff is not going away. You will see it again and again and again. You're going to see it in Calc 3. You're going to see it in differential equations. And then if you go into engineering, you'll see it for a long time there. Even if you became a math major, you'd probably see it still there. So in a very important operation, it's almost, it's almost like learning how to do addition all over again. But that'll be about it. Okay, so we'll leave it there, and we will see you next time.